Welcome back to our series on generating novel radar waveforms using GAN. This is part 3, where we dive deeper into the practical implementation of generative adversarial networks for creating unique and efficient radar waveforms. In this episode, we will start by generating new waveforms, followed by the evaluation of the generated waveforms. During the evaluation, we will cover key topics such as visualization, peak side lobe level comparison, and correlation analysis. Next, we will move to the conclusion, summarizing our findings. Finally, we will explore helper functions, including discriminator model loss function, generator model loss function, GLARE support for the ambiguity function, helper plot functions, helper plot ambig fun, helper plot correlation. Generate new waveforms. To generate new waveforms, use the minibatch predict function on the generator with an object containing a batch of random vectors. By default, the function uses a GPU if one is available. Create an object containing a batch of 25 random vectors to input to the generator network by using code here. Generated waveform evaluation. The waveforms generated by the deep learning network are evaluated visually, along with peak side lobe level comparisons in the range and Doppler domains. You can also perform a correlation analysis to determine the uniqueness of the generated waveforms. Visualization. Use the provided helper function to display the generated signal, along with its normalized ambiguity function in the first row. The second row displays the Doppler and delay values from a zero delay and zero Doppler cut through the 2D normalized ambiguity function of the signal respectively. The network generates waveforms with a similar ambiguity function shape as the training data. Multiple parallel ridges are observed with a tilt in the ambiguity function due to range Doppler coupling. The side lobe levels are also better in comparison to a thumbtack ambiguity function of random noise, where it is near zero level. The waveforms with a thumbtack ambiguity function are Doppler sensitive, but the generated waveforms are Doppler tolerant due to the tilt in the ambiguity function. Peak side lobe level comparison. The peak side lobe level, PSL, is an important metric in the context of radar systems. The side lobes near the main lobe are typically the highest. These side lobes can cause false alarms, and a lower PSL helps reduce the likelihood of such false detections. If the side lobes are too high, they can also prevent detection by interfering with the noise estimation of a CFAR detector. A lower side lobe would mean better distinction between closely spaced targets in range or velocity. The PSL analysis helps quantitatively compare the ambiguity functions of the generated and training waveforms. The average PSL comparison between the generated waveforms and the original waveforms from the training set without noise. Helper training signal, attached to this example, computes the original training waveforms without noise added. Use the attached helper function, helper display PSL, to calculate the peak side lobes, and display the difference in the zero delay and zero Doppler cuts across the training and generated waveforms. The PSL differences show that the network generates waveforms whose Doppler resolution matches the training waveforms. In the plot above, the PSL difference across the range resolution for a single waveform is 5.4 dB. This varies across the different training and generated waveforms, with an average difference of 9.2 dB. For the P4 and Zadorf-Chu training waveforms, the PSL difference of the generated signals is less than the average value in the range domain. The generated waveforms can replicate the Doppler resolution of the training waveforms more closely, in comparison to the range resolution. Correlation analysis. To analyze if the network can generate waveforms that are different from the training dataset while retaining similar ambiguity function properties, you can perform a correlation analysis. In the plot below, the first 6 signals correspond to the Frank, P1, P2, P3, P4, and Zadorf-Chu signals from the training set without noise added. Next 25 signals are generated from the deep learning network. From the correlation plot above, it can be noted that the generated waveforms are mostly different from the existing phase-coded waveform objects as they have low pairwise correlation with the first 6 columns. The correlation values vary between the generated signals, and this might be improved with further processing or training. Conclusion. In this example, you saw how to train a GAN network using a custom training loop to generate new phase-coded waveforms. This can overcome the drawback that there are only a limited number of code sequences of a specific length in most phase code families. By utilizing the ambiguity functions of waveforms like Frank, P1, P2, P3, P4, and Zadorf-Chu, this example shows how to generate novel waveforms of specific signal length. This can help meet the demands of modern radar applications. You saw how to view the generated signals, along with peak sidelobe level comparisons and correlation analysis. Here is the summary of helper functions and discriminator model loss function. Purpose: the helper model loss D function calculates the loss and gradients for the discriminator network in a Wasserstein generative adversarial network (WGAN-GP) model. Inputs: generator and discriminator networks. Mini-batch of input data. Array of random values. Lambda value for gradient penalty. Mini-batch size. Signal length. Signals PRF, pulse repetition frequency. Outputs. Loss value. Gradients of the loss with respect to the discriminator's parameters. Loss calculation. Ambiguity function. The ambiguity function of the generated signal is combined with the original signal's ambiguity function using a random weight. WGAN-GP loss. The loss is calculated as the difference between the discriminator's outputs for the real and generated signals, plus a gradient penalty term. Gradient penalty. Purpose: to improve stability and prevent discriminator collapse, a penalty is applied to gradients with large norms. Mechanism: the gradient penalty term is added to the loss function. Lambda value controls the magnitude of the gradient penalty. In essence, the helper model loss D function computes the loss for the discriminator in a WGAN-GP setting, incorporating a gradient penalty to enhance model stability. Here is the summary of generator model loss function. Purpose: the helper model loss G function calculates the loss and gradients for the generator network in the WGAN-GP model. Inputs: generator and discriminator networks. Array of random values. Mini-batch size. Signal length. Signals PRF. Outputs. Loss value. Gradients of the loss with respect to the generator's parameters. Loss calculation. Ambiguity function. The ambiguity function of the generated signal is calculated using the DL-AMBG fun function. Generator loss. The loss for the generator is calculated as the negative of the discriminator's output for the generated signal's ambiguity function. Mini-batch loss. For a mini-batch of generated signals, the mean loss is calculated. DL array support for ambiguity function. Purpose: to enable gradient computations on the ambiguity function calculations, the helper DL-AMGFun function is used. Functionality: the function returns the magnitude of the normalized ambiguity function for a given vector, sampling rate, and PRF. Deep Learning Toolbox. The helper DL-AMGFun function utilizes deep learning toolbox functions that operate on DL array objects to support gradient computations. In essence, the helper model loss G function computes the loss for the generator network in the WGAN-GP model, leveraging the DL-AMBG fun function and deep learning toolbox for efficient gradient calculations.